Have you ever wondered how we find the absolute best solution to a problem? You know, from training an AI to designing a power grid? Well, there's this surprisingly simple idea that makes it all possible, and it's called convexity. Today, we're going to dive into this powerful concept, and we'll be using Dmitry Persekis's incredible book, Convex Optimization Theory, as our guide. I mean, when you really get down to it, so many of the world's biggest challenges in science, in engineering, even finance, they all boil down to this one question. We're always looking for that optimal answer. But in a world with basically infinite possibilities, how can you ever be sure you found the one best solution? All right, so here's our game plan. We're going to start with what an optimization problem even is. Then we'll get into the magic of convexity with a simple analogy, the bowl. After that, we'll see why that gives us one true minimum, peek under the hood at the geometry, and finally reveal how this hidden tool is pretty much everywhere.
First things first, let's talk about the search. What does it actually mean to be looking for the best way to do something?
Okay, I want you to imagine any problem you're trying to solve as a giant landscape. The cost or the error of any solution you try, that's its altitude. So finding the best solution, it's really just like finding the lowest point in that entire landscape. Sounds easy enough, right? Well, not always. See, here's the catch. Most real-world problems aren't a simple, smooth landscape. They're more like a rugged mountain range, full of countless valleys. Now, if you just start walking downhill from wherever you are, you'll definitely find the bottom of a valley. We call that a local minimum. But is it the lowest valley in the whole range? Probably not. You could be stuck in a pretty good solution, while the absolute best one, the global minimum, is hiding just over the next ridge. And this is where our hero, convexity, enters the story. What if we could guarantee that our problem's landscape wasn't a mountain range at all? What if, by its very nature, it was something much, much simpler? So look at this. On the left, you've got that treacherous, non-convex mountain range. And on the right, a simple, perfect convex bowl. In that bowl, there's only one bottom. It doesn't matter where you start. Any step you take downhill has to lead you to that single lowest point. There are no other valleys to get trapped in. And that is the superpower of convexity. It literally transforms the problem landscape. So this incredibly simple shape gives us an almost unbelievable guarantee. This is where the magic really, really happens. And here it is, the crucial point. For any problem that has this bowl shape, if you find a minimum, you have found the minimum. The search is over. You found the best possible answer. Guaranteed. That right there is the aha moment. I mean, just think about what that means. It completely eliminates the problem of getting stuck. Instead of this complex, uncertain exploration, optimization just becomes a straightforward, reliable journey right to the bottom. It turns a problem that could be impossible into one we can actually solve, and solve really efficiently. Okay, so the bowl analogy is great, but what actually makes the bowl work? Let's take a quick peek under the hood and look at the simple geometric ideas from Persekis's text that give convexity all its power. It all starts with something called a convex set, and the definition is actually beautifully simple. A shape is convex if you can pick any 2 points inside it, draw a straight line between them, and that line never goes outside the shape. It's this simple property that stops any weird dips or coves from forming where a fake minimum could be hiding. Take these shapes for example. A circle, a square, a triangle, no matter which 2 points you pick inside of them, you draw a line and that line stays completely inside the shape. Simple as that. That's what makes them convex. But now look at these guys. A star, a crescent moon. You can easily find 2 points where the line connecting them actually pops out of the shape for a bit. And that's the dead giveaway. That's a non-convex set. So this same idea applies to functions. And this is what actually gives us our bowl shape. For a convex function, if you pick any 2 points on its curve and draw a line between them, that line will always be above or at most touching the curve. It never ever dips below it. It has nowhere to go but up, except for that one single minimum point. All right, so why does all this elegant geometry matter so much? Well, because this isn't just some abstract math concept. It is a fundamental tool that has literally built huge parts of the modern world we live in right now. This theory, which is captured so beautifully in texts like this one,
isn't just for mathematicians. The author's own work shows that it's an absolute cornerstone for engineers, for computer scientists, and researchers who are out there solving some of our toughest problems.
So where do we see this in action? Well, it is foundational for training so many machine learning models in AI. I mean, finding the lowest error, the bottom of that bowl, that's the whole goal. It's also crucial for managing how information flows in our data networks, making sure everything is efficient and reliable. From huge computations to dynamic programming, so many fields that define our era totally rely on the powerful guarantees that convexity gives them. So the takeaway here is pretty clear. If you can frame your problem as a convex one, you've basically found a massive shortcut to the best possible solution. But that leaves us with one last really fascinating question. What do we do with all those rugged, mountainous problems that you just can't smooth into a perfect bowl? Well, that is where the next chapter of optimization begins.